what I was then planning to do is I've got an overview presentation which takes you through all the lectures I've given very, very quickly, just saying, right, these are the key bits that I would really like you to concentrate on. And then I have a summary lecture which I can run through if you feel it would be of use. This is just simply going through the overview and then drawing your attention to which bits of the notes are important. Okay, so we can do that. Then the remainder of the time really is for the assignment, and the purpose of the session is if you've looked at the assignment and you've identified any issues, or there's any questions you've got that you want to discuss, then we'll do that then. I've also I've got a very brief presentation just to sort of take you through what are the initial start bits, which some of you may not find useful. If you've already started it, you might find you pass that. And then because this assignment is based on a real case, I've actually looked for some previous presentations that were part of the project that the operator carried out. And there's one or two interesting bits of them. The presentations haven't been set up for you as a group of MSc students doing the assignment. I'm really using presentation material that was prepared for the operator when the project was ongoing. It's been seen publicly, so I'm quite happy to go through it with you. Some of it's not relevant, some of it will just give you a quick overview of how the operator was dealing with it, which might be of some use. Okay, now anyone who, in terms of this session of the assignment, anybody who doesn't want to stay, who feels that, well, they're getting on with the work and they don't really need anything, please don't feel you have to say it. If you think it would be useful, then fine. Okay? Right, well, we better make a start. What this presentation runs through is, first of all, definitions of emergency incidents. Then we're going to look at emergency plans, procedures, and emergency response. Concentrate a bit on the operational procedures, because from a pipeline operator's point of view, they are obviously most important. And then we'll just cover briefly safety, and then training and testing. The majority of people who are involved in operations, their main contact with emergency operations is really this, because emergencies, if everything is under control and everything's stable, emergencies are in reality rare. So most people's experience of them and knowledge of them is based on training and testing, which is why that is so important. Okay, so we're going to concentrate on emergency operations relating to pipeline major accidents. These are high consequence but low likely events. Okay, and what that means is there are very few real occasions where the emergency arrangements are tested properly. And because the high consequence but low likelihood events, there's a general low level of awareness of the pipeline hazards and the risks, and that is particularly important from the operator's point of view, because in the event of an emergency or an accident, the operator is going to want to put their staff at the scene and involved with it. So that's a problem there. It's probably a bigger problem for the emergency services, because they will, in the event of an accident, they will take control of that, and if they're not aware of what could go wrong, then obviously that's an issue. Where you have a large-scale event which escalates very quickly, that means that various parties, and the main parties we're talking about are the fire service, the police, the ambulance service and the operator. They're the main services that we're talking about. They're going to have to mobilise quickly, they've got to coordinate, and they've got to work together. Now, if these are very low frequency events, they're not going to have much opportunity to practice that, so that is a problem. And what that means is that the requirement for emergency plans and procedures is very important. The whole purpose of plans and procedures is that they're there, people understand them, they're trained to use them, and once they're activated, you don't need to worry about managing people in detail. People should just go out and do things that they're trained to do without having a lot of detailed management. So that's why they're important. The typical issues which are associated with emergency operations is, first of all, there's a delay in establishing the cause of an incident. This will often be because incidents will be reported back through the emergency services or the pipeline operator's emergency number. They'll be probably reported by people who aren't used to reporting emergency incidents, so they won't use standard terminology, and whoever's on the receiving end of that will have to try and make a judgment as to what's going on. Local emergency services are often unaware of the pipeline or the consequences of failure. Okay, that is that's a bit unfair to say that that applies across the board, because if you're in a location where you have a lot of major hazard infrastructure, the local emergency services are normally very informed about what to do and what's there. If you're in a more remote rural area where perhaps the main activities are agriculture or whatever, the emergency services may not be so informed. So it does depend. In the UK, for example, areas like Teesside, Grangemouth, Stanlow over on the northwest, and in the southeast of the country, where there's a lot of sort of oil operator activity. Areas like that will the emergency services will be very informed, and they will be able to deal with things very quickly. In other areas, that might not be the case. Obviously, in the event of a major accident, there's going to be damage to infrastructure in the vicinity, and that could have other effects that need to be dealt with. And unfortunately, there's often experience of a disorganised response by the pipeline operator. And what that is normally associated with is delay in coordinating with the emergency responders. That's the police, the fire service. What you often see in the event of emergency, where ideally you would like all these parties to work together constructively and as a team, there's often conflicts between them and issues where one party or another is wanting to retain control. And there's often a delay in establishing the location of the failure. If you think about the issue with a pipeline, even if you have the best situation where perhaps the pipeline block valve separation is 16 kilometres, which is it's a fairly low level. In the UK, many of them would be much greater than that. And something's gone wrong somewhere on a stretch of pipeline, but you don't know where.
Sorry.
That's not quite right. We've just started. So the delay in establishing the location of failure is a problem. And then the other issue, which we talked about when we covered maintenance, response staff are often isolated. The pipeline is generally in a remote area, which means it's away from the control room. So in general, it's away from the staff base. And so wherever the incident happens, it's unlikely that you're going to have staff close to the location. So to deal with all that, what we need are adequate emergency arrangements. And emergency arrangements, when you see that, think about emergency plans and emergency procedures. The emergency procedures have got to be tested, reviewed and updated, and that's got to be a regular process, because you don't expect the emergency to occur frequently, and therefore if you don't do that, if it does occur, nobody will be in a position to deal with it. Competence of responding personnel, that's obvious. If you're called into an emergency or you have to deal with an emergency, you must be in a position where you're not having to ask questions about what you should be doing or what the infrastructure is doing. Emergency response in the control room is key. Alarm handling and communication with field personnel. That was what, if you remember, one of the incidents we looked at in the safety lecture was the Bellingham incident in America, which was one of the key incidents which caused the change in legislation in the US. That was a key issue there, and in fact if you read the report on the incident, it goes into detail about this sort of aspect. Leakage detection systems, big problem, because leakage detection systems, if you want to be in a position where you've got information, local information, accurate information, you need leakage detection systems. The problem with them is accuracy and stability, and if they're forever giving spurious signals into the control room, the tendency will be just to monitor what they're doing and not really respond to what they're doing. And then obviously you need effective shutdown procedures. Now, emergency incidents. What you find is that in all of the major hazard industries, they will define levels of emergency, right? These definitions are important because what they will do is trigger certain actions, and the actions that they trigger have got to be included in the emergency procedure, and people shouldn't need to be told what to do. If somebody triggers emergency level 1, then whoever's on standby to deal with emergency level 1 should know exactly what to do, and they shouldn't have to be calling people to say, I've had this notification, what do I do next? So the emergency incident definitions are very important because they will trigger a series of reactions which need to be carried out quickly, effectively and accurately. So let's just look at what we're talking about here. Level 1, which is again definitions of emergency incidents. The standard approach is that the lower the number or the lower the letter, you might have procedure levels A, B, C, or you might have 1, 2, 3. The higher the number, or the higher the letter through the alphabet, the more serious the incident is that you're dealing with. And the reason for that is once you've defined a level, and then you become aware that something else might happen and you have to introduce another definition, what you don't want to be doing is keep reorganizing your list of definitions, or everybody will get confused. So from a pipeline operator's point of view, level 1 is the lowest level of emergency, and what that's really mean is you've had some report either from the leakage detection system, or you've had an unconfirmed report of some sort of damage incident. Unconfirmed means that the operator hasn't confirmed that something's happened. So somebody thinks they've hit a pipeline and they've put in an emergency response. So that would be an example of the first one. Level 2 would normally involve the operator and the emergency services, and a typical example could be a fire which has occurred on a site, on a secure site. So if it's on a secure site, it's not affecting the public. If it's a fire, somebody could well have reported it, so it is likely to involve the emergency services. Level 3 would be a confirmed incident involving the emergency services and the operator, but no risk to the general public. Now, some of these incidents can actually be quite serious. Level 3 would normally mean that the emergency services have been notified first. Okay. And this is these photographs. They're very poor photographs because this is an emergency that happened in this area over 20 years ago. And these are just screenshots from the media coverage. So that's why the photographs aren't very good. But I'm sure most of you will be aware of the Western Bypass that goes around the west side of Newcastle. Now, what the site's actually been decommissioned, but close to the site there used to be a large array of underground high-pressure storage pipes. And what happened was, as the road passing the storage site, you can see on the top one, and what actually happened was there was an accident, essentially right at the edge of the site, where a lorry came off the bypass and went down the embankment. And of course Sod's Law was always operating, so the lorry actually landed on the rail track which skirted the storage site. So it looked like a very serious incident, and because it happened close to the underground pipe storage, the operator was called in by the emergency services. So that's and of course once that happens, the actual operation of the assets has to be restricted, just in case the incident escalates. Level 4 is where you've got a confirmed incident where there is likely to be risk to the general public. So you've got full mobilisation of the emergency services and the operator, and the emergency plan is initiated. Now, the only major experience I'm aware of, there have been others, but one particular incident that I was aware of as it unfolded was associated with one of the incidents we looked at in the safety lecture. This is the safety of a large gas pipe, the failure of a large gas pipeline close to the M74, which runs up into Scotland on the west side. The pipeline is very close to the road, and this really is just showing you, well, if you have an accident very close to a road, you've got a hazard range associated with that. And that issue, because the pipeline's close to the road, that scenario had been notified to the local authorities. So the actual emergency was called in by a member of the public. It happened quite late at night, and it was actually called in by a lorry driver who was passing on the road. That was called in to the police, and the police then activated the emergency plan, and it was quite serious at the time. They closed the road, they closed the railway line, and they closed Glasgow Airport. Right, so if you think about the knock-on effects of doing all of that, the costs that came back to the operator once it was, well, it was your asset, you caused the hazard, this is what it cost to deal with it. Those costs were quite high, so these things need to be dealt with as quickly and as efficiently as you can. Now, this particular incident we covered in the safety lecture. I'm not going to go through it in detail again. This is the Gislingham incident, which was a major accident which occurred on, it was actually a construction site, but there was operating pipelines going through the site. There was a huge fire. And I mentioned to you at the time there was a large number of fatalities. This is just an indication of the emergency vehicles trying to get onto site. So it was a major notification, so just about every emergency vehicle in the area was trying to attend. That generated quite a lot of chaos at the site, and there you can see the queue of ambulances waiting to get on the site to pick up fatalities and injuries. So organising response to issues like this is non-trivial, and of course the issue is, once you're in the middle of it, you want to organise it and you want to do it properly, but when it's just a theoretical event, you think, well, do you really need to do all of that? So let's think about how you start dealing and planning with it. Well, the first thing you've got to do is look at what sort of scenarios you might be dealing with, and in particular what types of emergency you may have to deal with and therefore have procedures for. The emergency plan is generally a legal, obviously it's a legal requirement, and it's the responsibility of, in the UK, it's the responsibility of the local authorities. Generally, in other parts of the world, it would be the responsibility of the local government organisation, whoever's got that responsibility. And basically, it's got two arms to it. One is the emergency response, which is always provided by the emergency responders. So that is always provided by the local government organisation. And then it's got the operator, and you can see that the operator procedures are going to be essential to what happens, the main one being shutdown, isolation, and then following that, repair and recommission. These two groups of people or two organisations don't work together very closely, and suddenly you've got a situation where they're forced to work together closely. So you've got to plan for that, and the way it's planned is you exchange information and you have to run tests. If you're going to run tests, people need to know what to do, so you've got to have training. And what you actually find in this sort of situation is the link between information and testing and training is quite close, because testing gives an opportunity to train. Okay? Right, the emergency plan. It's got to be clear and easy to understand. It's got to be flexible, because you don't know where you're going to have to activate the plan. It's got to consider the safety of the public, the responders, and it's also got to look at environment and economic aspects. It's got to very quickly allocate roles and responsibilities, and in particular the allocation of roles and responsibilities is probably most important between the emergency responders. So for example, in the event of a major accident, you would normally expect the fire service to take immediate control, and the other emergency responders have to basically report to the fire service. However, once the incident is under control, the police take responsibility, because it's their responsibility to get everything back to normal, because while you've got an accident going on, everything's disrupted and there's all sorts of knock-on effects. So you've got an obvious tension you can see is that the fire service are wanting to make sure everything's controlled and safe, whereas the police are saying we want to reopen all the roads, we want to make everything accessible again. Robust communication arrangements are essential. That's perhaps not quite the issue today that it was certainly a few years ago, simply because communication routes are so much better these days. However, the problem with communication routes at the moment is they're so large and diverse, and they're so easy to use, that you're maybe not quite sure where your communications are coming from and whether they're legitimate. So that's an issue that needs to be considered. It's got to address all credible major accident scenarios. It's got to dovetail with other relevant emergency plans, and it's got to include a restoration phase. So the purpose of the plan, the most important issue is to provide details of pre-planned response and method of operation to be implemented in the event of an emergency. Now, what you can see straight away is what that's going to do is tell all of the emergency responders and the pipeline operator, this is what you're going to do. And if any of those parties don't take on board that and actually turn it into their operating procedures and then train their staff for it, that is the first trigger for any disruption that could occur in the event of an emergency. It's got to allow control. You can't have, for example, I've mentioned a minimum of 4 parties that will get involved. That will be the fire service, the police, the ambulance service and the operator. What you can't do is have all of them saying that they're in control, or even that they're in control of part of it. It's got to allow a clear control route. It's got to define the communications, simply because you've got to know who you're talking to on the basis that you've probably never talked to them before, you've probably never dealt with the organisation before, so you've got to know what the protocol is. It's got to ensure prompt action, safe and efficient restoration of operation, and it's also got to ensure availability of personnel, materials and equipment. There's no point in having a pipeline emergency plan and then find, well, if you do actually activate it, you haven't got resources, you haven't got people, or you haven't got equipment to actually carry it out. Right, the emergency procedures. Obviously these are to mitigate the consequences. Once the accident's happened, you're into mitigation of what's happening. So in order to do that, you need to know what sort of hazards you might be dealing with. They've got to provide prompt response to the incident. And the issue here, in any sort of accident, the emergency responders will be prompt. They might not do the right thing because they haven't got the right information when they get there, but they will be prompt. The operator may not be as prompt. It's got to alert third parties, pipeline management, organise restoration work, minimise the effect on the local community. In other words, the last thing you do is drag people out of their houses unless you really need to, and it's got to rectify the cause of the incident. So let's just look at the interface between emergency plans and procedures. The emergency plan will define the responsibilities, coordinate individual emergency procedures, and in order to do that, there's a number of items of information that are needed. And so in terms of a pipeline or a response to a pipeline accident, you can see that the local government authority is going to be doing this, but in order to do it, it needs all of this. So you've got to put a responsibility on the pipeline operator to provide all of this information to the local authority or local government organisation. And then the emergency procedures, in particular the operator ones, have got to specify which activities have got to be carried out, who's going to carry them out and how, and then you can see the typical procedures that that will needed. The other thing that emergency plans need to do is they need to identify and use existing procedures, right? So the emergency responders will all have their own internal procedures about what they do in the event of an emergency, and what you can't do is change those procedures. Does that seem obvious to everyone? Because it's very important. If you're expecting people to respond quickly and essentially automatically, you can't then suddenly change what they're expected to do. So the last thing you can do is have an emergency plan which could cut across the emergency responders procedures, or not take account of the pipeline operators procedures, because all you'll end up with in that situation is chaos. So to think, the emergency plan will eventually it will eventually focus on the emergency response and basically say, well, in the event of an emergency, this is what everybody's got to do. So if you just have a quick scan of that list, you can see where the interface with the operator is going to be very important here. The operator needs to inform of the failure modes and consequences. It's the operator's duty to determine the associated hazard distances that might be associated with a release. In reality, it's the operator's duty to do this, but you often find that's the first source of conflict between the operator and the emergency responders. The emergency responders like to take responsibility for this because essentially they are the ones who will take decisions about evacuation and shelter of people. But potential problem areas, is the operator is probably in the best position to be able to do that. Obviously, geographical areas where you could have a problem, in particular problem of access. The identifying the nature and extent of resources that may be needed in the event of an accident. I mean, actually, just on this one, geographic areas where you might think a geographic area is going to be a problem if you can't actually get emergency equipment to the area. If you go back to thinking about the Gislinghine incident, that was in an area which was centred on an industrial development and had not been flagged up at all as having any problems with access. It had a big road network around it, and it had there was clear signage about where the facility was, and all of the emergency vehicles and then all of the local traffic got completely snarled up in the response to the accident, and that was what generated a lot of the injuries. Communications protocol we've talked about, and obviously one of the issues here, which these two are linked, documentation of emergency contact details along the pipeline route. Because emergencies don't happen very frequently, if you're ever doing an audit of operator procedures, you can guarantee that when you look at their emergency procedures, you'll find lots of gaps and holes and things that haven't been updated because they never use them, and it is a problem. You know, you you pick up the emergency communications procedure and you find that the person at the top of the list died 20 years ago, and that is typical of what happens. Okay, so the information you need to prepare the plan is actually quite straightforward, and we've covered a lot of this. Well, we haven't covered details of planning distances, but we've talked about hazard ranges, and we've talked about the types of hazard associated with different types of product. Right, now the communication system has got to be simple and brief. The problem with communications systems being brief is that people develop lots of acronyms so that they can say things quickly over mobile phones or radio systems, and what that means is there's very few people who actually understand what they're saying, so that is a problem. Recording of information is very important. Modern emergency communication systems rely heavily on mobile telephones, and what that meant at one time, I'm not sure what the position is now, but at one time that meant that in the event of an emergency, the local mobile phone network would be immediately taken over so that it was available for use in the emergency. And of course that happened in the Buncefield incident, which happened in the UK, I think was 2005. The local emergency phone network was taken over so that there was clear communications between all of the parties. And what that meant was that a lot of the local people couldn't use their mobile phones because they were inactive. So there's all sorts of issues. But the main communication requirements are receipt of emergency calls, notifications, and responsibility for liaison. Technical data. If you just scan that list, you can see that the technical data, this is the technical data that the emergency responders are going to need when they're responding to the incident, and you can see all of that is pretty straightforward. Right, in terms of the emergency plan, you've got to look at worst case scenarios, and this doesn't necessarily mean thinking about the worst sort of the absolute worst disaster that could happen. But if a bad situation occurs and you're not prepared to deal with it, then that is a serious flaw. So, for example, if you look at worst case scenarios for pipelines conveying flammable fluids, the worst case that you would probably have to deal with would be an unconfined vapor cloud, which would lead to an explosion followed by a major fire. So if you think that's the worst case, you've then got to look at the extent and size of the cloud, the dispersion concentrations, the overpressure which could occur in the event of the explosion, the explosion would happen in the event of ignition, and therefore if you got an explosion, what would be the overpressure you would deal with, and then the safe distances for people. And of course the issue in this worst case scenario, the big issue you're dealing with is the source of ignition is unlikely to be at the point of incident. So dealing with that thing is a problem, and that brings you into topography of buildings and the effect that has on gas dispersion. Toxic substances, of course, toxic substances probably provide the absolute worst case scenario. Right, emergency procedures. The first thing they do is identify responsibilities, list named contacts, include safety management, access to specialist services, and interface with the local authority emergency plan. Sorry about that. It's obviously one thing you shouldn't do, leave your mobile phone on. And the key issue with emergency procedures is testing and review and update, because it's unlikely that you'll be using them regularly. Incident response. Obviously, the incident response is going to track back straight into these aspects of the procedures. The operational procedures that we've listed before are shutdown, isolation, hot work, for example, the types of hot work that Gary covered last week, inspection and damage assessment, repair and recommissioning. While all of this is ongoing, you need to think about safety and environmental hazards. So there's a list of those that need to be considered and dealt with. That list is like the sort of list you might get from a kind of brainstorm exercise. You can see that it's not ordered in terms of priority or importance. Safety requirements. Predominantly dealing with the hazard and protecting the people who are dealing with the hazard. And one important aspect of emergency procedures is the management of damaged pipelines. If you've had a report that a pipeline is damaged but isn't leaking, then the issue you've got is, well, it might not have failed now, but could it fail in the immediate future? In particular when people are working on it. So what's absolutely essential as part of this is procedures for management of damaged pipelines. I keep meaning to redo that slide because it's not very good, but basically all it does is show the cascade that needs to go on once an emergency call is received by control room. This is assuming, this slide's not very good because it assumes the emergency call is going to come into the operator. And if it's a low level incident, it may well come into the operator, but if it's a significant incident, it won't come into the operator, it'll go into the emergency services at some point. And then this slide is really just to give you an indication of how quickly things escalate and become complex in terms of managing, and also the level of acronyms that start to develop, and you know, the fact that somebody responsible for in the local government emergency planning office may understand everything on that slide. Very few other people will, and yet it's the people on the ground who will be trying to deal with the situation.
Regarding the first one, not this one, the previous one.
Sorry?
Previous graphic.
The previous
Slides.
one.
Yeah, I think this one is for the operators, yeah?
Yeah, this one is assuming that
control room operator received the signal and he will do the step by step.
well, basically, what if it did come into the operator's emergency control room? This is what they would have to do. These are probably not correct, because in reality they would have to notify, they'll have an emergency services contact, and that emergency services contact will be responsible for basically doing all of this.
No, I mean, I think this is one correct, because the thing is, it's a step for the control room operator. In order to, for example, he needs to control the police.
Yes.
The second thing, he needs to control this, contact with fire department and other things. I think it's only for the operator opposite. Procedure for operators.
Yeah, absolutely right. That's why this isn't a good slide, because it's basically saying, well, in the event of an emergency call coming into the operator's control room, what does the controller do?
Yeah.
You're absolutely right, and therefore in that response, in that respect, it's only a very limited aspect, and in reality, the situation looks more like this, much more complex, much more confusing, and much more difficult to control. So that takes us back to testing, reviewing, and updating. Now, obviously, there's a number of things that you've got to take into account here. First of all, the fact that the local infrastructure is going to be changing, changes in response technology, lessons learned from previous incidents. That's actually quite difficult to do. People don't do that terribly well. Lessons learned from the application of plans during accidents. Well, if we think about it, we talked a lot about the Bunsfield incident and the Gislinghine incident. There are still papers being produced about what was learned from those incidents, so it does take a long time. Big problem is changes in personnel, particularly now, because you find that people don't often stay in one position for too long. Right, so training is important because these events don't happen very often, and when they do happen, you expect people to deal with them. So you've got to train them, and that means that you've got to basically expose them to real events. So, for example, in the UK, the organisation that does a lot of that is the Fire Services College, where they actually run what amount to real life incidents. You've got to have people have got to be aware of incident terminology. So in particular, the obvious incident terminology they've got to be aware of is the definition of the level of incident. They've got to understand the plans and procedures. They must understand how to interface with the emergency services, and that is particularly important because the emergency services are set up to deal with this sort of thing, and they deal with a lot of emergencies all the time, a lot of low-level emergencies, and they are generally, I think most people would agree, the emergency services are very aggressive, and if you don't know how to deal with them, then they will basically take control. They'll run rampant over all of your staff and all of your issues, and in doing that they may get it wrong, and once they've got it wrong, particularly if they get it wrong and the incident escalates, they will come back and say it's your fault. So it's very important that you deal with them properly. And obviously the bottom line is sharing of good practice. Right, media. Or any emergency response plan is going to require a procedure for dealing with the media. And there's a number of issues that you need to do. The media will, if you don't control the interface with them, they will take control of how they're informing people. But you've got to deal with them because the media will be the fastest route of informing the public. Okay, so if you use the media properly, you can actually deal with the initial aspects of the emergency very quickly and effectively, which means you've got to deal with the media so that they don't issue lots of things that could frighten people, because when people are frightened, they won't behave in a controlled way. But you can get information to a large area and a large number of people very quickly. Okay, the number of considerations that you would need to take account of when you're developing emergency plans and procedures. And then there's, this is a typical tutorial question, which means really how I expect you to deal with this information in terms of an exam. So, obviously, explain why emergency level definitions are needed. Typical examples. The examples are fairly straightforward. Explain the purpose and objectives of the emergency plan and the emergency procedures. What information is needed, what activities, interface with the media, what's the purpose of regular training, and why is a procedure for management of damaged pipelines required, and what does it cover. The most important bullets there are the first two. Okay, we'll be coming on to that again when we go through the overview and summary.
Question. Do codes and standards give guidelines on the emergency operations?
Who?
The codes like ASME or the...
Right, well, all of the codes basically put the duty on the operator to have emergency procedures. In terms of the wider issue, you need to go to legislation and the various sort of communications that come out of that. So if you look at all of the operator pipeline standards, they will all say that you need emergency procedures. But then the requirement for the testing of emergency procedures, etc., that is in legislation.
I understand it's important to establish the cause of failure in case there is a major failure. So how do we do that? Because when a failure happens, the pipeline it explodes. And so how do we establish the real cause?
Well, that's a good point. In reality, probably the organisation which has the best procedures to go in and do that would be the safety regulators. And essentially what they will do is as soon as they can actually isolate the area, they will take control of it and they'll basically start collecting forensic evidence. That's why the operator needs very close liaison. And it's a good point actually, because I haven't mentioned the safety regulator. If you think about all of the major accidents that are showed in the safety literature, right? The safety regulator took control of the site and then started actually taking away parts of the failed pipeline and setting up independent examinations of those. And they also then immediately go in and interrogate the operating procedures for the pipeline. And by that, I mean what the control room was doing at the time. So what records of the control room got. And so it's done as essentially a huge forensic exercise. It normally takes a long time. I mean, the pressure is always on to say something fairly quickly about what happened and why it happened. But to do it properly and to get it right normally takes time. I mean, the way in which it's done is very variable, and I think probably the people who are best at doing it are the Americans. If you look at their safety regulator sites, they will issue reports on failures in a series of stages. The reports are well constructed, and they're very factual. You find, certainly in Europe, people get very caught up in the legislative side of it, legal responsibility, legal privilege, and they don't actually, there's a real clampdown on releasing information. So probably in terms of an incident that's happened, the first sources of factual information would probably come out through the safety regulator. Right. I just need to decide what to do now. At the beginning of the lecture, what I said was in terms of this session. There's 3 things I want to do. The first one was to go through that lecture. Second one is to go through an overview of the lectures that I've given you, and then I have got a summary lecture which just goes through the overview and then points out in the notes I've given you, these are the important bits. I'll only do that if you want it. It's not necessary. And then the final thing is to return to the assignment. Now the session on the assignment is down to you really. I would like to be able to offer you any help that I can. If you've started on the assignment and you feel that you want to just get on with it in the way that you're dealing with it, then please don't feel you need to stay for that session. I'm going to go through some high-level points which I think are, if you haven't started the assignment, well, here's a quick kickstart to it. And then because the assignment is based on a real project that happened, I have brought some material that was prepared by the operator and was presented to the technical community and to the safety regulator at the start of the project. And that, a lot of it's not relevant to what you're doing, but some of it shows you the kind of issues that the operator identified that they needed to think about. Okay, so what I suggest we do is, rather than spend time on the hot tap and stopper at the moment, I'll go through the overview, and then if you think it would be relevant, I'll go through the summary. I think the summary's probably got enough in it for you to see the issues associated with the hot tap and stopper. The information Gary provided was more than what you require, but you need something to be able to revise before the exam. That's my only concern there. So if we do that, and then we'll take a break, and those of you who want to stay for the assignment session, then you stay, and those of you who feel that you can use the time better elsewhere, obviously. Okay, so before we have a break, we'll go through the overview and the summary. Right, so what I'm going to do here is basically give you a quick overview of the topics that I've, or that if you like, are on my agenda for dealing with in this course. So that covers the safety lecture, now not the whole of the safety course, obviously just the safety lecture that I gave. surveillance, operations and maintenance, hot tap and stopple, and emergency ops. Okay. Right. So in terms of safety, the issues that I asked you to concentrate on during that lecture was how do the pipeline standards control the failure frequency and the consequences of failure? Okay. What are the pipeline failure modes? You should be able to answer that very quickly. What are the pipeline failure modes? Absolutely, right. So pipeline failure modes, very important because they will actually control the consequences, or they'll influence the consequences. And what's the other issue with rupture? Do you remember that one? Good one, yeah. And why is it so? The issue with rupture is what's in the pipeline. Does everybody remember that? Ruptures look different if you've got liquids. Absolutely, right, okay. Then what failure modes actually, what failure modes do specific damage mechanisms generate? And again, I've got that in the summary if you want to look at it, but basically some damage mechanisms you only really expect to produce leaks. Some of them will definitely produce ruptures. Okay. And then the difference between the failure of gas and liquid pipelines, which you've just covered. Okay, right. Surveillance, inspection, and maintenance. So, in this, what I've done is pull together essentially 2 lectures, because it was in 2 presentations, and there's 2 sets of notes associated with it. But the overall topic is surveillance, inspection, and maintenance. All right. So the key thing about surveillance is why do you do it, how do you do it, and when do you do it? Okay. We said at the time it's a very important, it's probably one of the most important activities the pipeline operator has to carry out. So how do they do it, why do they do it, how do they do it, and how frequently do they do it? And then associated with that, what data is observed and recorded, which basically means if you're looking at the route regularly, you're expecting to pick up changes. So what changes are you looking for? And then which things might have been observed or recorded that then cause the operator to carry out further actions? Okay. Pipeline and installation, inspection and maintenance. The issues here are what activities are we talking about and what are the frequencies of the activities. Okay, and then finally, what factors that should say must be taken into account when setting frequencies. Right, so fairly straightforward stuff, and as I say, we can go through it in a little more detail if it's useful. Right, hot tap and stopple. The key issue here is the hot tap and stopple procedure. Okay, so what I'm particularly interested in, how do you deal with the situation? What do you do if you've got a situation where you've got to carry out some hot taps because you're going to carry out a stoppling operation? Bearing in mind that not all hot tap operations require a stopple. In some cases you might not be wanting to stop the flow, you might just be wanting to tap into it. And then emergency operations. What are the emergency levels and why are they needed? Okay, so it's fairly straightforward. Yeah. What's the purpose of the emergency plan and what's the purpose of emergency procedures? Right, okay, so do you want me to go through the summary?
Yes.
Right, okay, but please bear in mind, these lectures aren't on Blackboard.
I'm not.
No.
They are not.
No, not these ones that I'm giving you now.
Emergency levels.
The emergency levels. Oh yes, the emergency information that definitely will be on Blackboard.
Not the summary.
Not the summary, and not this lecture. Everything that's in this lecture you've already had. It's in the lectures that and the notes that I've given you. But this particular lecture isn't on Blackboard, and it won't be on Blackboard, and I'm sure you really understand why. Okay. Right, so the first thing I said that I wanted you to concentrate on was how do pipeline standards control failure frequency and the consequences of failure? What are the pipeline failure modes? What failure modes do specific damage mechanisms cause? And what's the difference between the failure of gas and liquid pipelines? Right, now the main slide here, and I'm not expecting you to learn this slide by rote, okay? What I'm expecting you to do is to be able to look at it and say, right, well, these are the key sections in a pipeline code, right? If you pick up any pipeline code, it will start, it might not call it plan, but it will talk about the requirements for the pipeline. It will go into design and materials, construction, commissioning and acceptance. Then it will cover operations, inspection and maintenance, and in most cases codes will cover revalidation, replacement and abandonment. And for each of those sections I've tried to indicate what the key controls are that the standard is putting in place. All right, and that is in the notes pack that you got. Then I gave you a couple of slides which basically said, right, we're going to minimize. I said that all of the pipeline standards, the aims of them are to minimize failure and to mitigate consequences. So they're the aims. So how do they do that? Well, in terms of minimizing the frequency, then what they do is they try to avoid material and construction defects, and they do that by requiring technical specifications, and in particular the pressure test, the pre-commissioning pressure test. They control degradation, and in particular that is the design and installation of corrosion protection systems. They ensure pipe resistance to resist the majority of likely impact damage, and they do that by wall thickness and any protection measures that are required. And they control the operating stress of the pipeline by controlling the design factor. Okay?
Sorry, how many questions are you going to ask in the
Well, I actually contribute to half of a safety question, and then I do 2 full questions on the exam, which is set at the end of this module. Right, minimizing the consequences of failure. The codes do that by the selection of the location of the pipeline, and generally that's how the code classifies the location and how it deals with the population and infrastructure around. So in the UK codes, they will classify the location as class 1, class 2, or rural and suburban, and then the ASME code basically starts from class 1 through to class 4. Routing, having identified and classified the area, the pipeline, the codes then basically provide guidance in routing through areas of minimum population and infrastructure, and in doing that they specify the distance from the population and infrastructure, and the intention there is to minimise the numbers of people, the development, and therefore numbers of people in the vicinity of the pipeline. Causes of pipeline failure, fairly standard causes. These are the typical causes which are listed in all of the failure databases. The key ones are material fabrication, construction defects, external interference, corrosion, natural causes, or incorrect operation. And then there is always a category other, which is a catch-all for everything else that might happen. And then which damage mechanisms cause which types of failure. The key thing here, this picture is really giving you a typical breakdown of all of the causes, and this one is saying these are the causes which will definitely result in ruptures. Okay, the majority of these failures will be leaks. Okay? And then we discussed some pipeline failure modes. The leak is a stable defect. The rupture is an unstable defect which will extend during the failure, and the extent depends on whether you've got a liquid or a gas. It basically, it's dependent on the compressibility of the fluid which is in the pipeline. Right, so coming on now to surveillance, inspection and maintenance. These were the points that I said were I would like you to pay attention to. So the purpose of surveillance, the main purposes are to assess population changes in the vicinity of the pipeline and to identify activities which could pose a threat to the pipeline. In particular, anything to do with land management or construction, and also to identify any environmental issues which could apply loading to the pipeline, such as floods and ground movement. Surveillance. Essentially, this is all surveillance activities. The most important ones, which were covered in the surveillance lecture, but are probably better laid out in this slide, which was in the operations and maintenance lecture: aerial surveillance, vantage point, walking surveys. What do you do in them, and how frequently do you do it? Okay, so that's pretty straightforward. Inspection. The main issue with inspection of pipelines is internal inspection and external inspection. Okay, so actual physical inspection of the pipe wall, which is inline inspection, and external inspection or condition monitoring, which is monitoring of the CP system and SIPs and DCBG surveys. Okay.
So here we have a question regarding this past paper. Discuss the prevention and mitigation methods that might be included in integrated management process to address the threats, external corrosion, internal corrosion, and third-party damage. So in this question, for example,
And I actually recognise that question. You saying that's one of my questions. Right, okay. There's a lot of overlap in this module. There's a lot of overlap between what some of the lecturers cover. So certainly some of the material I've covered, and that's not one of my questions, but yeah, the information is relevant to that. Right, pipeline installation, operations and maintenance activities. Now, this aspect is essential, but it's tedious, and I have tried to simplify it and put the information in tabular form. The main issue here is on any site, you're going to have to do routine routine checks, functional checks, and overhauls or aspects of mechanical maintenance. So I've tried to summarise that, indicate which equipment is relevant and the frequency that you would do that. We covered the frequencies in that. So I'm not looking for very complex and analytical assessments of reliability-based or risk-based maintenance. The bottom line is, as a pipeline operator, you're responsible for a number of installations, so what is a minimum do you need to have in place to deal with them? Don't think you need, well, the only thing that's important here actually is this one, which is the condition examination, and that's to do with the fact that on any high pressure pipeline installation, any aspect of deteriorating condition could eventually lead to a loss of containment incident. So that monitoring condition is important, and you normally do that at a very basic level by carrying out visual assessment. The visual assessment should identify any damage and deterioration, and that should then trigger any more detailed inspection that you may want to do. Right, I've then I'm certainly not suggesting for 1 minute that you need to learn these lists, but what you do need to know is, well, basically, what's the difference between a routine check and a functional check? So we covered the example lists of what sort of things you would do. You don't need to learn these lists, you just need to have a feel for what sort of activities you would undertake in routine checks. Similarly in functional checks, so bottom line here is, what's the difference between a routine check and a functional check? Okay. Factors affecting maintenance frequencies. The issues here really are the site characteristics. If you have a remote site, a remote unmanned site, the tendency will be to visit the site as on a minimum possible basis. And in order to do that, you need to take account of, well, what sort of telemetry have you got in place? In other words, can you monitor it remotely? Is it critical to the performance of the system? Is it sensitive to any environmental factors? Like, for example, if you suddenly have a very low temperature, could something affect the site, and therefore should, following a low temperature weather incident, should you go and check it? And bottom line is it secure? Routine checks are generally associated with the security of the site. Okay, so if it's in a very remote area and it's pretty secure, then you'd think, well, do you need to visit it every month, or could you extend the frequency to 2 or 3 months? And then in terms of telemetry, it's a question of how much telemetry you've got in place. There should always be a minimum level of telemetry you've got in place, because you will have to operate a SCADA system on the pipeline. But for some sites you may have much more. You may be monitoring inlet, and you might even be controlling inlet and outlet pressure. You may be monitoring inlet and outlet temperature, and you may be controlling outlet temperature by triggering the heating system, monitoring the flow rate. You may be monitoring the filter differential pressures, so you know when the filters are actually going to need attention, and you have got full monitoring and control of the slam shut position and its action. Right, hot tap and stopper procedure. Obviously, Gary covered all of this last week, and all I'm going to do is take you through some slides which are on the notes which I put on Blackboard. Right, so hot tapping is you're drilling into an operating pipeline to get access to it, and stoppling is you're plugging the pipeline temporarily so that you can do something to either modify or repair it. So the procedure, very simply, is this list of activities. Now I need you to actually have a better handle on it than just this list, but the list is important because it's very easy to miss one out. So you've got to think about the preparation. The preparation is basically digging the hole, checking the pipe, etc. Installing the tees, carrying out the drilling operations, fitting the bypass, inserting the stopples, undertaking the work, recommissioning the isolated section, withdrawing the stopples, removing the bypass, and then locking off the stopple entry points. Now, on the in the notes that are on Blackboard, I've been through each of those and actually put a fairly reasonable description of each of them. Okay, so hopefully that means that the key factors in each of the stages of the procedure are actually there, so that you can see why they're important. Lots of engineers would actually prefer to use diagrams rather than lots of words, and so annotated diagrams are totally acceptable. So if you were going through, as long as you get all of the stages of the procedure, okay, so you don't miss any of the key stages out. It's quite acceptable to do it as a series of diagrams. So the key thing on the first stage is to expose the pipeline, and the most important thing is you've got to properly support it, because you're going to be applying some quite significant loads to it. You've then got to install the tees, which you're going to use to get access to the pipeline, and obviously the vent points. You've then got to identify what you want to do with each of the tees. So this tee, the tee's on the outer side, so obviously this is just half of the diagram. The tees on the outer side you're going to use to fit the bypass to. The next ones you're going to use to insert the stopple, and in the notes that are on Blackboard, the next tee was generally used as a bag hold tee. Now, Gary, actually, the issue here is the double block and bleed requirement. Okay, so and this procedure was developed primarily by the gas industry. So the issue here is if you put a stopple here and it doesn't quite seal, and you've got leaking pressurized gas coming through here, one of the easiest ways to stop that would be to put a flexible bag in that you can then blow up so that it takes the proper. Now, Gary, in his lecture last week, he talked about other more robust double block and bleed procedures. You know, he talked about using stopple trains, etc. So that's in the issue there is that the stopple plug should be a double block and bleed requirement.
So regarding this backhoe, is this one also valve? Is it backhoe also?
Sorry?
The backhoe, what is it? Is it the valve?
Well, it would be a tee that you would then force a sealing bag into. Remember, the tees give you access to the pipeline. So what this is saying is, in this procedure, as a minimum, you need to cut into the pipeline to install a bypass.
Yeah.
So you're going to need 2 locations for that. You're going to have to cut into the pipeline in order to plug it. You're going to need 2 locations for that. And then you're going to need, you need to ensure a double block and bleed.
You can put double, I mean, here will be like, you have one stopple there, and then back hole, it might be also the bulb. And between them you have a vent bulb.
Yes.
It might be also that you can use it as a double block and bleed in that piece.
Yes, yes, you could. So this is...
Why you need to put another in the back hole and another double block and bleed?
No, you wouldn't. That there is your double block and bleed.
Yeah.
And if you, if for example in here, you inserted a stopple train as Gary showed you last week, and you vented between the stopples, that would give you the double block and
I
bleed.
mean the back hole actuates should be the lock itself, another lock, another stopple.
Ideally, yes, but yes, you are right. The concern at the time when these procedures were evolving would be if you've put a stopple in here and it hasn't quite sealed, you put another stopple in there and it doesn't quite seal, you've still got an issue. Whereas if you put a flexible bag in and you blow the bag up like a balloon, provided you haven't got a massive leak going past this stopple, you should be able to deal with it. Okay, so then we move on to fitting the bypass, inserting the stopples, and the issue here is, the important thing here is getting the sequence right. So you've got obviously an upstream and a downstream stopple position, and you would always start the procedure at the downstream location. Then you undertake work, and the key issues for undertaking work, and this is talking about bags, use of bags. The issue is double block and bleed. So, you know, if in your procedure you said you ignored the bag hole and said that the stopple would be inserted to provide double block and bleed, the issue is dealing with the requirements for testing for leakage and purging. And again, I've included an idea of installing, covering all of that with diagrams. The diagrams, you can do the diagrams in any way you like. The diagrams don't need to look like these diagrams as long as they're understandable. So if you're going to use diagrams, no problem at all. Just make sure that you annotate them and so that the diagrams are easy to follow. And then finally, recommissioning the isolated section, which means essentially removing everything and purging and fitting the locking plugs, then withdrawing the stopples and removing the bypass. And as Gary emphasised last week, the important issue here is to remove as much as you can from the pipeline, because whatever you leave on the pipeline is then going to be part of the pipeline for its future operation and could affect the integrity of the pipeline. So the approach is always to try and remove everything that you can remove. And then this is a diagram which really basically explains the locking flanges.
Sorry, regarding the integrity, you mean removing, you mean inside the product, inside?
No, the issue is, if you think about it, before you start the operation, you've got a length of pipeline, which is just the pipeline, okay? Then you do this operation, and as a minimum, you're going to leave the T's on the pipeline, okay? Because you welded the T's onto the pipeline so that they provide you with a full pressure containment location, so you can't take them off, okay? But whatever you can take off, you take off. So for example, you've got a T with a bypass connected to it. You don't leave the bypass there, you take the bypass. off. Okay, so whatever you can remove, you do remove. And this is basically just showing the procedure for locking. So we've got these specific locking flanges, which Gary covered in his presentation. They've got an O-ring in them for a seal. So these locking flanges are inserted essentially using the what was the stoppling arm. So they're pushed down into the T. The O-ring provides an immediate seal, and then you lock the ring into position, which basically means that it's got a ring in it, which you then screw in the connecting parts, which are part of the flange. So what that means is the locking ring itself, when you remove the sandwich valve, the locking ring itself will contain the pressure. It's got to be able to retain the pressure, because you've got to get the valve off before you can put the final flange on. So this locking ring, in reality, its purpose is to provide pressure containment while you disconnect all the equipment and actually then apply the final sealing flange on the T. Was that okay? And those notes are on Blackboard. I'll check with Naracon. I'm sure some of you have already seen the notes I haven't put new notes on for this year, because the notes that are there for last year cover all of that. The notes will cover more than what I've just gone through, but it's what I've just gone through which is important.
Regarding this locking rings, so you're saying it's I cannot imagine how it's fixed to the
Yeah, now I might actually, hang on a minute. Right, I'll try and show you. This sequence of slides is actually very good, and it comes originally from TDW. All right. Right, so we're talking about the plugging off procedure, okay? So what you've got to do is get the plug into the branch of the T. You've got to lock it in position and have it all sealed before you can then take everything off and apply the final flange. So the plug has got to be lowered through the valve, so the sandwich valve is still in position. Okay, it's got to be lowered through that into the essentially the flange connection, which is connected to the T-piece itself. Okay, and obviously there's this. What you're actually doing, you're putting this in as pressure containment, so you've got to be able to equalise the pressure over the plug while you're doing it. If you don't do that, there is a chance that the plug might not seat properly, so you could end up not having it actually inserted properly. Okay, so once you've got the plug in place, you then open the valve and you push the plug down into the T. Okay, so here, this is the sandwich valve, and you can see the sandwich valve has got these flanges on it. This flange is connected to the T.
So actually, it's not screwed there. It's like seal it and fix it.
That exactly, yes. So, but it has got a groove in it, right? And you are going to have to screw connection points into this groove to hold it in place.
Is it like a woodwork paper and stuff?
Sorry?
Is it like a woodwork paper? Just quite slow.
Yeah, yeah. So essentially this flange here, when you take the sandwich valve off, that flange needs to be replaced by a blank flange over the plug. So essentially the plug is being used for pressure containment while you disconnect all of the equipment. Okay, so once it's in position, you then drive the screws into the groove. So basically what that means is when you take all of this equipment off, you're not just relying on the O-ring to make the seal. Which means you can then bend down and you can expect the plug to actually hold the pressure differential. You can then take the valve off, take the plug holder off and put the blind flange on.
Are those screws part of the T?
Yes, those screws are part of the T which you are plugging off. So these T's, these hot tap T's are actually quite specialist components. And in fact, I think there's a complete ASME standard which is dedicated purely to the design of hot tap T's.
Yeah, they have the dedicated hole with a seal. The screw, these two holes, it is for screw.
Yes, yeah. These here.
No. This one. Yeah.
Yes, yeah. They're basically indicating that you're screwing in. Okay, so basically, this is what I meant earlier. You've got to get to the stage where you've only left on the pipeline things that you can't really take off, and that whatever you've left on the pipeline is secure. And one of the issues that does happen with a lot of these connections do leak, and if they leak, if as a result of not installing them properly they leak, then you've got an ongoing maintenance issue to deal with.
So that would be the ideal scenario, right?
Sorry?
That would be the ideal scenario.
Absolutely, yeah. Right, okay, so I'll just quickly go back to the final bit of the... Okay, so basically the aspects of emergency operations which I would like you to concentrate on are the emergency levels and why they're needed, the purpose of the emergency plan and the purpose of the emergency procedure. The emergency incidents are there. Why are they needed? I don't think there's a specific point on why they're needed in the slides, but I think we discussed in quite a lot of detail why you need these things. In the event of an emergency, you haven't got time to do briefings, provide instructions. You've basically just got to expect people to follow procedures and to know what they have to do. And therefore, your emergency procedure has got to immediately tell people what sort of incident they're dealing with. Purpose of the emergency plan.
Sorry, regarding this question, why you need the emergency plan, can I just write your answer? Let's say, in case of emergency, you don't have time to briefing, that's kind of thing.
Absolutely, yeah.
And I will get full mark.
Oh, you'll get full marks of however many marks are allocated, absolutely. No, I mean, but it's not a lot of this is important factual common sense, and you need to understand it, and you need to demonstrate. When answering the exam questions, you need to demonstrate you understand it, and that doesn't mean going into lots and lots of wordy descriptions in many cases. For the information that I've covered, most of the stuff I've covered is basic and factual, and I'm not expecting essay type answers. Okay? Right, so the purpose of the emergency plan, there's some key bullets there. Now, if I've given you information like this, and then I ask for, well, what's the purpose of the emergency plan? I might say expect 3 or 4 points. I'm not expecting regurgitation of lists.
So
but
if I write like provide the details and of Red Planet and allow the control and define communications, there's just 3 of them. So I will get full marks.
yeah, well, put it this way. I
don't
would
need to justify them, yeah?
no.
Okay.
No,
So this would be enough like this, yeah, for example, 3 lines or 4 lines.
Yeah,
Oh.
yeah. Now, if, for example, you see that come up in an exam question, and you think, well, actually, I can easily put 6 points down, but I'm only going to put 3. Well, that would be a bit silly, wouldn't it? If you can easily put 6 points down, put 6 points down. But I'm expecting you to put bullet points down. I'm not expecting you to go into lots of detailed explanations.
Because some markers, they mark how many lines you wrote.
Yeah.
Oh, who said that?
Yeah.
They
I
mark
think
like
that's
that.
semester.
You wrote 15. You wrote 15 lines is not enough. You wrote 14, 12 lines is not enough.
Well,
Or
you
you wrote
might be
50.
20 and there might be rubbish.
Yeah, that's what I'm saying.
No, you might write 15 lines with
So I said the same thing, but that guy he pays attention how many lines did you write.
Right, well, my experience of marking exams is there's nothing worse than getting to a page and a half of a response to an exam question. There's absolutely nothing in that that you can award a point for.
And the thing is, referring to the level 7. Level 7, we have this standard education, and we have some levels.
Yeah, level. And I see it's level somewhere.
Right, all right, okay, I'm not familiar with that, so.
It's good. Yeah, it's okay.
What is level 7? Is level 7 how examiners should be marking questions?
Yes, something related like that.
Some kind of procedure.
No, it's your bachelor's degree, you have level 5 when you finish your
Depends on
marker.
It depends on marker.
That's okay. It will be level 7.
Right,
When you do a PhD, level 9.
Right,
That kind
right.
of thing.
Right.
Level of education, actually.
Okay, that's fine. Well, for each of those levels, there will be a level of knowledge demonstration the student has to demonstrate. And that demonstration, how the student demonstrates that will depend on the subject they're covering. And what I'm saying to you is, in the subjects that I'm talking to you about, I'm not expecting essays. I'm certainly not going to mark exam questions based on how many lines you do. But equally, if there was a question like that, and you put 1 line down, then the chances are you wouldn't get full marks, okay? And to be honest, I don't remember how many points I've asked for, but I won't have asked for all of them. But any of them that you remember, that you can write down in the exam, you should put down, shouldn't you? You should never try and avoid the opportunity to collect marks in an exam. Okay? Right, so similarly we've got a list of bullets which are to do with the purpose of the emergency procedures. Right, so that's basically a summary of what I've given you. Is that okay?
Yeah, thank you very much.
Okay, right. Well, it's 11:15 now. I'm sure you need a break. I'm going to be around until 12. If you decide you want to cover the session on the assignment, whoever comes back for the session on the assignment, we'll cover what I've got. If you feel that you've used the time better doing something else, then by all
Is
means.
this one is today the last day of the year?
Yeah.
Yes.
Oh.
Yeah, so if you've got any difficult questions, you should really ask them. In terms of the assignment, what I have said to to narrow corners. If you start getting into the assignment and you feel that you need another essentially like tutorial session on it, if you ask him, he will organise a session for you to come in.
Last week that he's going to say us in the middle of when we do something.
Yes, right now I should have checked the emails to tell you when it's due, and I haven't. What I have done, he's asked me to run through the marking scheme with you, so I'm going to do that. But I've forgotten to check. I'm sure it's the 27th of April, but I will send Narracorn an email after this lecture and ask him to make sure that the submission date is on Blackboard.
It's a lot of things to do. We need to keep saving the lives of
I appreciate that. Right, okay, so
when I was studying the, can we come back like?
we'll aim to start the next session about 11.
Кстати, в прошлом году ребята последний второго семестра когда заканчивали? Когда последний? В мае или июне? Или до июня? До июня, я думаю, закончимся.
Yeah, I was gonna tell you.
Some style.
Yeah, some style. Like that, yeah?
Are you crazy?
He's teaching me how to work sexy. In a sexy way, yeah.
You guys are crazy.
He's teaching me. Show me.
Like a big man.
But how am I working? Richard, give me that. Ah, no, I can't.
Maybe July, yeah, last day of July. I usually for long, about 3 months, they finally Korean court of impeachment. Blood.
Those are very nice shoes. Where do you get Well, I got this. No, it's not.
꼭 봐야겠다 싶어.
제대로 하는
Once you get like music, like shine stuff. Around 60. But not all that is glass. So glass are not you remain professional. Yeah, I want you to I would never take advantage of the situation. Well, not only the glass, but maybe the it's different because, for example, the thing is that I wouldn't like to treat that because I wouldn't like to treat someone like I ran into the doctor yesterday. He said that I did a very good job in the course. materials. What else?
No, I didn't ask about that. Again, like, we just were talking about the project, about the dissertation. We're going to start. I'm going to start training the next week. He was having his he was having his move.
I just approached you to say hi. So they know that if you
More than
How do you know that? You are weird.
The thing is that I would not do this. It's a nice one, it's nice. He's just around the corner. He's right next to you. You mean like it's just like a bar with different quite private. No, it's near. I would say that it's in the street of the gate. Yeah, and before you get to the cathedral. Yeah, before you get to the cathedral, there is a well, no, it's around.
Sorry, regarding this question, I think this is your question, if I'm not wrong. This one, yeah? The first two questions, is it yours?
No, to be honest, the whichever one is mine varies from year to year. So
We can use this one.
15 group.
right, that's my one.
Mexico is right between Mexico is right between Korea. Why not? Mexico is fun.
Mexico, you have a lot of
Check on this.
drug violence.
It might be 1 or 2.
But
Which I think is probably what you were asking before.
just close. This thing are almost outdoors.
No, well, they do exist now, and they have some problem.
They have like
That's
Call it,
yeah, so in that paper it was 1 and 6.
Yeah, the problem. Well, the thing is that you don't
some of them is also overlapping it.
Yeah, I mean there are overlaps in this, and the external lecturers have pointed out to the university if you're going to use external lecturers, you should really make sure that they actually know what people are doing.
We got El Chapo.
So, explain.
El Chapo. No, El Chapo is like Escobar.
Yeah, I wouldn't worry too much about it. You've seen the way I teach before. If I thought that was I would draw it. So,
Respect. Exactly.
What are you going to do this weekend?
For this one, yeah, so we need to just say
When I set that example, I had done the exploratory class, basically to take through the concept, showing them the kind of calculations that we needed. But that's supposed to monitor that question on a year-to-year basis, so you make sure that you're changing them. So I do change them. Right, should we make a start? Okay, on the change of use assignment, the marking scheme that's going to be applied is here. So basically, these are the aspects of the work that are going to be marked, and these are the marks that are going to be allocated. So the report, the main thing is, sorry, apologies for the spelling mistakes. The issue with the report is it needs to be a professional report, okay? You need to think that somebody is paying you to do this work and they're going to look for a good report. So I'm looking for the structure of the report. The presentation, is it neat? Is it well laid out? Is it easy to follow? So essentially that means it's going to need an executive summary, okay?
Like an abstract at the beginning?
Essentially, yes. Yeah. Because particularly executive summaries are very important, particularly when you're doing work for money, because the client will read the executive summary to find out if you've delivered to them what they ask for, and they'll form a view based on the executive summary. So executive summaries are very important. They don't have to be very long, but they are very important. Okay. You need to include references. You know, any kind of professional work that you do in which you are providing an opinion or a judgment back to the client, you've got to explain what you're basing your judgment on. And supporting appendices. We talked last week about we've just started, about the fact that you don't need to put, in my view, you don't need to put lots and lots of information in this assignment. But there may be some information that you feel needs to be in the report so that the client can fully understand what you've done. And essentially the skill in doing these reports is deciding what you put in the main body of the report and what you put in the appendices. If you put too much in the main body of the report, people, particularly non-experts, might get lost as they're reading the report. They might think, what on earth is all this about? However, if you feel the information is important, it should go into appendices, so that if anybody comes back later on and says, oh, I've suddenly found this aspect's important and you didn't cover it, you can say, well, yes, it's in the appendix. Okay, so that's all to do with how you go about constructing that. Next thing is the methodology. We covered this really last week. The methodology, how do you go about changing the use of a pipeline? What things need to be done, and how have you used the standard? So I'm expecting there the presentation of how you've done it, your explanation of the requirements, and the logic you've applied. Okay? Now, if it's really clear and straightforward, you might get away with doing that as a sort of algorithm, a logic diagram. You can do it however you like, but before you do any work at all, whoever's reading the report needs to understand what you're doing, and therefore what they need to look for in the report. The next two sections are really how you've assessed the information that's been given to you for the assignment. And I've separated it out in terms of the route assessment. Whenever you're doing anything on a pipeline, and this could be anything from new design right through to integrity review, revalidation, change of use, uprating, whatever you're doing, you're going to have to go through the route, and you're going to have to consider the route in terms of what's there now. And that means you've got to be able to follow the route map, and you've got to identify any key features that are on the route. And by key features, the key features are things that the design code will tell you you've got to either design for or consider. Crossings, special crossings would be the main thing. The other issue would be developments, occupied buildings, etc., close to the pipeline. Okay, and so in that, I'm looking for how you've reviewed and commented on the route data and how you've identified features along the route. And again, I'm looking for you to apply judgment. I'm not looking for you to go down, every 100 meters of the pipeline and make a comment on what's there. I'm looking for you to look at the route and to identify the key features. All right? Next thing, this is important, calculations and interpretation. As we said last week, there are a number of calculations that you need to do. Those calculations are all essential for you to demonstrate compliance with the code requirements. Okay, so you've got to do the calculations, and you've got to try and get them right. Okay, now getting them right might depend to some extent on the assumptions that you apply, but if I can understand the assumptions that you've applied in doing the calculations, and those assumptions are correct in terms of what the code tells you to do, then that's fine. But I'm talking here about the maximum allowable operating pressure, the design factor, the BPD, and the minimum distance to occupied buildings. Okay, the TD1, the pipeline at the moment is compliant with TD1, and TD1 talks about building proximity distances. In the future, if you change the use to CO2, it's going to have to comply with PD8010 Part 1, and that talks about minimum distance to occupied buildings. They're both essentially the same thing, but you calculate them differently. Okay, so you've got to do those calculations. Fatigue, and then in doing all of those calculations, you've got to, the interpretation bit is essentially why you're doing them and how you're complying with the code requirements. Okay? And then finally, discussion, conclusions and recommendations, and bottom line here is the change of use feasible? Are there any limitations? What are your conclusions, and what recommendations are you making for further work? Okay, so there's quite a lot of scope there for you to take the problem and for you to deal with it and produce what you think is the right response to the problem. But there's at least some guidance there as to where you're going to get the marks from. So, for example, if you do the whole thing without looking at the pipeline route or doing the calculations, then you're going to lose 20 out of 50 marks. Okay? Is that all right? Okay, so now just going through some of the things that I think are essential to get you started on the assignment. Let's look at the calculations, what the calculations that you've got to do. To me, that's the important bit, because as a minimum, you should be able to do these calculations and get marks for them, right? So it is important. First of all, the maximum allowable operating pressure, and there's two things that you need to consider here. One is the phase diagram, and the other is the PD8010 pressure diagram. So let's look at the phase diagram first. The issue that this is covered a bit in one of the operator presentations. I'm going to show you. Basically, CO2 is quite a complex material, and basically it exists in either vapor phase or liquid phase, and also then once you've gone past a certain pressure, it will exist in the dense phase, and at high temperatures the dense phase is called supercritical. But essentially, whichever phase you decide to operate in, you want the material to stay stable. Okay, so you don't want to be setting operating conditions which mean that the fluid could change phase in operation, because that's just going to give you loads of problems. So in the information that you were given a temperature range that the pipeline would operate at. That temperature range immediately allows you to relate the conditions of the CO2 back to the pressure. That's going to define the pressure that you can operate on for the pipeline that you're dealing with. Because remember, this pipeline exists. If you were designing a new pipeline from scratch, you could say, right, what is the best way of dealing with CO2 in accordance with this phase diagram? You haven't got that luxury because you're using an existing pipeline. So you need to look at what are the pressure limits for the pipeline as it stands at the moment, and how do those pressure limits relate back to that phase diagram. And as I say, I've got a little bit of information on that in one of the operator presentations. Right, the PD8010 pressure diagram, basically what this defines are a number of pressure conditions, and you need to review those to identify which ones are important. And in particular, you need to look at you need to look at items 3, 4 and 5, because you are redefining the maximum allowable operating pressure, but you've got to relate that back to what 8010 is dealing with as a design pressure. Okay, and you've then got to think, well, it's as you would do for any pressurized system, you've got to identify a maximum incidental pressure. So you've got your maximum allowable pressure, which is what you can operate to all the time, but because you're applying control systems to actually control that pressure, it will fluctuate. How much fluctuation are you going to allow? And most of the pipeline standards will tell you what you can allow as a maximum, and in general it's 10%.
Is it state a low pressure also for the old pipelines? I mean, when we are really using the...
Yes.
There is the requirements for the old, yeah?
Yes, for this. I mean, you can think about that, and you can make a point in the assignment. The issue with pipelines, with gas pipelines, right? And this was a gas pipeline, okay? When you pressurize the pipeline, you've got to assume that the pressure could be anywhere in the pipeline, because gas is compressible and it's a bit like a sponge. You know, whatever you do at one location will eventually transfer to another. If it's a liquid pipeline, you will get pressure gradient, right? Because the liquids, particularly if they're incompressible, then they will be higher pressure where you're pumping them, and they'll be lower pressure where you're taking them out. So you will get a pressure gradient, and for that reason, in many cases, liquid pipelines will have different design conditions along their length if they're long pipelines. Okay, so you might have thick wall at the start where the pressure is going to be high, and you might have thinner wall at the other end where the pressure's dropped by the time you're taking it out. So you can consider things like that, and this diagram does consider that sort of issue. Okay, I suggest you don't get involved in it in too much detail, but you've got to show that the maximum allowable operating pressure that you're recommending complies with PD8010 Part 1. So you've got to refer to that diagram.
This test, the pressure test, are we going to do the pressure test?
Good point. Well, that's what you need to think about. We'll come on to that in a minute when I go through some things, but it's a very good point. If you're changing the conditions of any pipeline, you're essentially restarting a new design life.
Yeah.
Okay, and a requirement for starting a design life is a pressure test. So, do you need to do a pressure test, or is there something about this particular condition that you think, well, actually we don't need to do a pressure test?
Is MAOP related to the pressure test?
Yeah. Yes, it is. So you certainly need to consider it, but the key issue here is, if you're changing use, and the pressure is either the same or lower than the previous pressure, do you think you need a pressure test?
No.
If it's higher, do you need a pressure test?
Yes.
See, it's basic principles like that that you need to just say, well, you know, and you need to present these principles authoritatively, right? The code is allowing you to, so you don't present them as if there's something that needs to be argued about. It is a code principle, and therefore you use it. Okay?
As long as we justify our answer, will that be alright?
Yeah.
So,
Yeah, yes, absolutely, provided you get it right. And remember that this is being marked against the requirements of the pipeline standard. So if you come up with something that doesn't agree with the pipeline standard, then obviously it's not right. But the pipeline standard will give you some scope for interpretation, and you're entitled to use that. Right, now calculations. You need to calculate the design factor. Calculating the design factor is in both TD1 and it's in 8010 part 1, and I'll tell you now that the way that the two codes tell you to calculate it is exactly the same. Both codes tell you that you've got to calculate the design factor using the minimum pipeline wall, the minimum wall thickness, which means you've got to check the manufacturing tolerance. And what I suggest you do is you decide what the pipe material is, and because this pipe was first commissioned in 1978, what would be a standard large diameter high pressure pipeline in 1978? Well, it's going to be a seam welded pipe, isn't it? So you need to look in API 5L and check what the manufacturing tolerance is for that, and then you need to apply that in the calculations, because in the information that you were given the nominal pipeline parameters. Okay? Right, now the BPD in TD1 we looked at briefly last week. There is you've got the design section for TD1, and there's a figure, I think it's figure 5, I can't remember, but figure 5 gives you the BPDs for high pressure pipelines, and it gives you the equation for how to calculate the BPD for the pipeline. So you've got to calculate the BPD in accordance with TD1.
Sorry, please, what's the formula of BPD?
Sorry?
The formula of
The formula for BPD is on the figure in TD1. So if you're not happy with that, I'll have a look at it. I'll have a look at it in a moment. But if any of you've got that section of TD1 with you, if you could perhaps pull it up, and then we can check. But the formula, which is very simple, it's just a simple straight line formula.
The full meaning of the acronym BP.
Oh, right, the building proximity distance, right? So BPD is building proximity distance, and MDOB is minimum distance to occupied buildings. They are exactly the same thing, they're just called different things in the different standards. Right, so we talked about the BPD in TD1 last week. It's done slightly differently in PD 8010. The reason it's done differently is 8010, TD1 applies only to natural gas. 8010 applies to all other fluids. Okay, so obviously 8010 needs to handle it differently. And the way it does it, it presents this equation for Y, in which Y is the essentially going to be the MDOB, and it calls up a substance factor, and the substance factor essentially is a multiplier which is taking account of the hazardous nature of the fluid. And it then gives a table which includes substance factors. All right, and it's got 2 substance factors for CO2. It's got 2 factors which are informative, right? The reason they're informative is at the time this version of the code was produced, the government actually provided money for the update to include CO2 pipelines because they were giving grants to operators to look at building CO2 pipelines. And the 2 and 1 were actually recommended by the work that was carried out by National Grid.
So if you
But
choose it to operate at a dense phase, then you go for 2,
Yeah.
2.0. If you choose to operate at a gas phase,
You use 1, absolutely.
So we have a temperature range.
Yeah.
And after calculating the maximum allowable operating pressure, it determines whether we operate in either
Yeah.
dense and there's nothing we can do about that.
yeah.
No, there's nothing you can do to control the phase diagram. The only way you could control the phase diagram of CO2 would be to control the operating temperature of the pipeline, which would be very expensive. Right? The pipeline exists, it's in the ground, it's buried. Its temperature is going to be predominantly dominated by either what's in the pipeline or the ground temperature.
And for this particular assignment, we are already constrained by the temperature.
Absolutely. Yeah.
So there's no giving it.
So for this, there's table and calculation. So then we calculate the exit, this partial distance from the actual pipeline.
Sorry, I can't quite.
When we calculate for the exit, the partial distance for the current natural gas
Right.
pipeline.
Exactly. You've got to calculate the GMT because that tells you what has been controlled around the current pipeline.
You mean
If
based
the
on the KPIs?
Yes. So if the operator's been operating it to TD1 and it's compliant with TD1, they'll have been surveying the pipeline and they'll have been checking that nothing is causing an infringement on the route. Okay. Now, if you do if you calculate the minimum distance occupied buildings according to 8010 for CO2, and it's greater than that distance, that immediately gives you a problem because you're going to have to deal with a wider route, and the operator won't have been controlling anything which is outside the current route. So, if the distance you calculate is less than that distance, then you're probably okay. So these are the things you need to think about.
So excuse me, because what if the new distance now that you get for the PD, it's not complying with what we have in
Well, no, that's a good point. If the distances are different and you've got to do something, then you need to think about, well, okay, how do we move to the new distance? You might need to look at that. If there are infringements, you might need to look at changing the water system, putting in protection, changing the surveillance. So all of the issues will consider in that, all apply in that respect. Okay. Right, the next thing are the fatigue calculations. In the information that you were given, there was some cyclic pressures associated with previous operation, and you need to calculate the fatigue damage using the SN curve, which is in TD1, which basically gives you the SN curve, and then it gives you the simple damage equation for where you've got more than one pressure range to take into account. What you've got to do is calculate the damage fraction and decide, has the pipeline seen any significant fatigue damage in previous life, and has it got enough scope to see fatigue damage in its future life. Okay, so you'll need to make some assumptions about the potential pressure cycles that it could see. All you've been told is that it is going to operate for another 15 years. So you then need to make a decision about the fatigue for the next 15 years. You just need to make a straightforward engineering judgment, and you need to explain what you've done. Okay? Right, I'm just going to quickly show you, run through a couple of presentations. This particular presentation was right in the early days of the of this project. National Grid produced a number of conference presentations, and basically what they were doing was saying, right, well, we're going into a new area. This is what we're doing. We're going to tell the technical community what we're doing, and if anybody thinks we're doing it wrong, they should come back and tell us. And we're going to interface with the regulator and tell the regulator what we're doing, so that if anybody's got a concern, they tell us now and we can deal with it, rather than we get to the stage where we've changed the use, we're operating a CO2 pipeline and everybody has problems with what we're doing. So that was the process. So this was quite an early presentation that they gave. Sorry, I forgot to take the animation out. So what they're basically doing is they're looking at what's different for CO2 pipelines, what knowledge, codes and specification are needed to design, construct and operate and maintain a CO2 pipeline system, what's currently available and what research needs to be done. So that was where they were at the time. And they presented two project interests. One was in Scotland, the reuse of existing assets, and it was a single pipeline which was basically going to give a new point-to-point solution. It was going to collect CO2 from one location and transport it to another location, and that included some short new pipeline sections which needed to be built. And they decided, now you've got the pipeline parameters, they decided it had to be gaseous phase, and this, I'll at least explain some of that. I'm sure you would have come to that conclusion yourselves, but let's just see what the operator was doing. And then in England, they were going to do a new build pipeline network, and that was going to be a mixture of gaseous and dense phase CO2. So this is the Scottish one, and basically what they were doing, they've got three large diameter pipelines which come down to southern Scotland from St Fergus, and those pipelines were installed at the start of North Sea oil in the UK, North Sea gas in the UK. So the key requirement was to get lots of gas down from St Fergus down to England. So they built these large there was actually 4 pipelines, 3 coming down this route and another big one which went down that route. And because the supply of gas in the UK has changed and they now don't need as much gas from St Fergus, one of these pipelines can be decommissioned or could be its use can be changed. And so they decided they were going to use one of these pipelines to collect CO2 from Long Gannet power station and transport it up to St Fergus, and then from St Fergus it was going to be pumped offshore for storage. So that was the that particular one, and basically it's a fairly simple scheme in which this is the new section of pipeline, because obviously the gas system isn't connected to the power station at the moment, so new section of pipeline required. Then the pipeline, this is the existing pipeline which goes through a number of installations, and it was it then needed to be connected through another new pipeline to a compressor facility which would then be used to essentially pump the CO2 offshore. Right, so here's the first key. Obviously they did a number of assessments. What they wanted to do was get the best use out of this pipeline. However, they decided that the maximum allowable operating pressure was going to be 32.5 bar, which allows an incidental pressure of 35.5 bar. And it means the design factor is 0.3. So that was the decision they came to. That doesn't need to be the decision you come to, but it's only reasonable to let you know what was going on. I won't spend a lot of time on this particular one. This is a much more complex scheme, which was to do with linking a number of power stations and industrial outlets into a network in which they were going to collect in the gaseous phase and take into a spine pipeline and then operate that in the dense phase and pump out to the southern North Sea. Right, so let's look at what they said about existing pipelines. From their point of view, using an existing pipeline is a fast track because one of the longest phases in getting any pipeline development is getting the routing agreed and getting all the planning permission installed. So if you've got something which is already in the ground, that's a fast track. They were intending to use pipelines that are no longer critical for natural gas transmission. Operation in the gaseous phase involves pressures lower than the original design and current operating pressures. In other words, 35 bar against either 70, 84 or 85. The reason they've got those pressures there is they've done upratings of the pipelines that I'm talking about in order to meet peak demands in the late 90s. The pipelines are subject to the application of existing natural gas standards. So we now need to look at the requirements for change of use and revalidation. And that means identifying technical gaps. And the technical gaps that they identified at the time were the route corridor definition, separation distances, BPD versus minimum distance to occupied building, and the QRA methodology, because obviously the QRA methodologies which exist, which are very robust at the moment, tend to be for fluids which pose thermal hazards, not fluids which pose toxic or asphyxiation hazards. Okay, so essentially you need a new QRA methodology. Right, I'm not going to go through that in too much detail.
Sorry. Do we have available report for this?
I sent some papers to Narracorn to put on Blackboard for you. I only sent them last night, so you probably haven't seen them yet. But he wrote to me last night and said they're now all available on. So there is some stuff, and some of these papers are produced by National Grid. Some of them are also produced by Newcastle University, because Newcastle University was involved in the research at this stage. Okay, some of this is just standard operator stuff. Okay, what this sequence is doing, they're basically saying the big issues with pipelines are all things we know about. The big issues are construction, getting the pipeline in. That's the expensive bit. We've done all that. We know all about the pipeline we've got, etc. The issue there is if it complies with TD1, can it comply with 8010? Right, here they're going on to say existing pipeline codes do not fully address or define the requirements for CO2. Now remember, I've told you to use PD 8010 Part 1 2015, and that includes updates to allow it to apply to CO2. But at the time when National Grid was saying this, that hadn't happened, and the work that National Grid did as part of these research programs was fed into the pipeline standard. So the issues they identified, and some of these things might be of interest: decompression, dispersion, phase boundary, specification, hydraulic analysis. Okay, anything where you've got a phase change, hydraulic analysis becomes very important. The material requirements, if it's going to operate in the gaseous phase or the dense phase. It's going to be compressible, and therefore arrest of ductile fracture is important. Risk levels, what affects on people, and that affects the routing guidelines. Now, you can't apply routing guidelines to an existing pipeline, but what you should do is say, well, if you were applying routing guidelines, how would they apply to this pipeline, and could you get this pipeline to comply with them? And then the pipeline operation, maintenance and integrity management, inline inspection activities, etc. And there was a number of issues here. One was the issue of inline inspection tools getting stuck in CO2 pipelines because of the nature of the CO2 and how that affected elastomers on the pig. And the other issue is CO2 and water produces carbonic acid, which is highly corrosive. So obviously you've got, you're moving from operating using sweet dry gas to carbon dioxide, which, because you're collecting it, the state of it actually is down to what you say it needs to be. Because it's coming out of a power station, you can then say, right, what state does it need to be in before it gets in the pipeline? Okay, right, so these were the items of work that National Grid was basically starting at the top. The need for the pipeline and public consultation, you don't need to worry about that too much. That's not part of your assessment, but it is something that causes pipeline operators. I mean, obviously, if the need for the pipeline is to do with, are you actually going to get the right amount of money for operating it? So that's quite important. Public consultation is what you don't want is to have a major public reaction to what you're doing, because that'll just stop and delay and perhaps prevent you operating. Right, but now let's look at some important technical things. Design. These are most of the issues that I've asked you to look at. Design factor, area class, routing, hydraulic analysis. We'll just think about that in a minute. If you do gaseous phase, you're not really going to have to worry about a hydraulic analysis because it's going to be a gas. However, if there's a possibility you could change phase, you're then straight into hydraulic analysis of liquids, and that is a much more onerous situation to be in. Block valve spacing, remote actuation, metering, corrosion prevention. They were all issues that, as an operator, were identified that needed to be considered. You don't need to consider all of them in what you're doing. I've asked you to do a straightforward, pick up the codes and say, is it feasible? Once you've decided it's feasible, you may well have to look at some of these issues in quite a lot of detail. Material requirements. The two key issues were arrest of propagating fractures. In other words, the pipeline currently is adequate for arrest of ductile fractures under natural gas operation, so is it going to be adequate for CO2? And then the other issue, it's already been recognised that CO2 has a deteriorating effect on elastomers, which means it could affect valves, any sort of operating equipment that you're using on the pipeline. QRA, construction, testing. Key issue with testing was drying requirements, and the issue there is you don't really want water mixing with CO2. Commissioning, they saw the issue with commissioning as being how do you get volumes of CO2 in, and how do you control the phase of the CO2 while you're doing the commissioning. And then operating and maintenance, the issues identified were how do you make sure it's dry? How do you deal with inline inspection? What emergency procedures do you need? How do you deal with depressurization, venting, blowdown, all of which are things you may have to do in the event of an emergency or for maintenance. And then personnel and training and competence.
Could you please repeat what do you mean by volumes in commissioning?
Basically, when you've got a two-phase fluid and you start putting fluid into essentially an empty space, it's going to go to the conditions of its lowest pressure. Then as you start pumping up, it could change condition, and that gives you a problem in commissioning. So when you're dealing with any fluid which does that, you've got to have quite a complex commissioning phase. Maybe not an issue if you're going to stay in gaseous phase, but if you're going to move to dense phase, it certainly would be. Right, okay, so this is the interpretation of the phase diagram. Okay, so this is a simpler version of what I've shown you. So I'm basically saying, right, here you've got solid, here you've got vapor, here you've got dense phase, and there you've got supercritical. And basically, in reality, from an operating point of view, you want to be either there or there. Right, so what they're doing here is superimposing the allowable operating conditions of the pipeline as it exists at the moment. So there's the temperature range. In fact, I think I gave you a temperature range of 4 to 13. So the range I gave you is actually narrower than this range. But what they're saying is, in that range there, you could get two-phase behaviour, which you want to avoid. So what they identified was, right, well, we don't want two-phase behaviour. You need to investigate and interrogate why they decided they couldn't go to dense phase. You need to do the calculations. That's simple design factor calculation. Okay, the critical point is 73.9 bar. So basically, in order to be to ensure you're in the dense phase, you're going to have to be greater than 73.9 bar. The pipeline at the moment is operating at 75 bar. They decided, right, we can't let it go over 38 bar. Okay. Then what they were saying was, well, in the absence of code rules, we're going to have to develop them, and they were the issues that they were looking at. Right, I've got another presentation which I won't go through in full, but some of it is quite right. Now this is the work. Right at the start of this project for National Grid, they put a contract with Newcastle University to do some investigations, and basically it was a 5-task research program that they asked Newcastle University to carry out. First of all, determining the specification for CO2 purity, dryness, material requirements, implications for pipeline design in terms of existing codes, and hydraulic modelling. Right, now there is one of the papers that I've asked Narracorn to put on Blackboard. It was published at IPC by the team that were doing the work at Newcastle University. You may find, actually, if you look around, you may find that they published more than that, but that was a good introductory paper. And so basically here there are some conclusions. So this is the conclusion they came to in terms of CO2 purity. And the issue here is, well, most of the experience on CO2 pipelines comes from America, and that is predominantly associated with pure CO2. In terms of what the UK was interested in here, it's what they're calling anthropogenic CO2. So it's dirty CO2 that comes out of power stations or industrial processes. It's got other things in with it, and those other things could certainly have an effect on the equation of state. In other words, they're going to affect the phase boundary, and they're also going to affect the how corrosive the
Now,
fluid is.
do you assume it's pure CO2?
No, you can't assume it's pure CO2.
Because the phase diagram of the distance.
Right, okay, good point. At the moment, you use the phase diagram that I've given you. The phase diagram will be different. You don't know what the changes to the phase diagram are because you don't know what the CO2 is, but you've got to flag up that it's an issue. Okay, which is one of the reasons why when National Grid were interpreting the phase diagram, they were putting limits. They were basically saying, we're not going to take this to the limit of the phase diagram because something might happen that mean we've got to have a margin.
Is there any other diagrams available?
There are diagrams available they'll be in yes, that are available in the research. They're actually quite complex, and I'm not for 1 minute suggesting that you get involved in a detailed assessment of changes to phase CO2 phase diagrams because it's a research topic in itself.
So we just could say, assume it's not pure, but we could use the diagram you have given.
You use the diagram that I've given you, and you draw attention to the fact that if it's got other substances in it, that might change. In fact, these conclusions are actually good. I haven't put this on Blackboard, but I'll summarise this presentation and I'll put some of these slides on Blackboard for you. It was work that Newcastle did, and I'm sure if you looked around you'd probably find research papers that were published on it. Right, so here they're talking about the purity of CO2, and what's interesting here is what they say about gaseous phase CO2 pipelines. Water solubility is reduced, and therefore you need more stringent drying. In other words, if there's water in the CO2 stream and the CO2 is gaseous, the water is going to drop out and become free water in the pipeline, free water exposed to CO2. So that's not something that you want to be dealing with. Right, material requirements. Issues here are upset and fault conditions might change the level of water that's in the CO2. So you could have specified a level of dryness, and you could have an upset condition, which means water gets in. So what does that mean in terms of corrosion? What about H2S? Certainly a lot of the CO2 which comes out of power stations could have H2S in it. H2S, of course, at a certain limit will switch you from a sweet condition to a sour condition. And then obviously they're drawing attention to the impurity levels. Then they looked at fracture propagation. One of the papers I've put on Blackboard covers the initial thoughts on fracture propagation. They're also covering elastomer seal materials, and basically what they're saying is you've got to make sure your elastomers are tolerant to CO2, which is particularly important, of course, for valves. Design to existing temperature. Now, what Newcastle University said at the time was there's no provision in the UK for coverage of CO2 pipelines, and what they identified, these are the issues, because the codes don't cover them, these are the issues you're going to have to think about. So again, you know, a good list of points. Right, now this Newcastle University actually undertook the first hydraulic analyses of feeder 10, which was the pipeline going from St Fergus to southern Scotland that National Grid had intended to use. So what they said was that first of all they looked at flow rates for different compositions. So they're looking at different impurities in the CO2 and saying, well, actually that doesn't make a great deal of difference to the hydraulic analysis. Low flow rates are gravity dominated. So density has a significant influence, which basically means the pressure profile between your high points and your low points could be a problem. They actually calculated the maximum pressure difference for supercritical cases, which means they're talking about pressures above 73.9 bar. The pressure needs to be maintained above 73.82 bar for the best case scenario, which means it's got to be in the dense phase, and it's got to be kept above 86.69 bar for the worst case. So that what they're saying is, well, if we look at what the impurities could do to the phase diagram, they're going to shift the phase the line up, and that means that actually you're going to have to operate, to be safe, you're going to have to operate at a higher pressure than just what's indicated at the phase diagram. And then since 86.89 is greater than the MOP of the pipeline, supercritical transport is not feasible. So that really is where the original decision for National Grid not to go down that route actually came from. Most of this I don't think you need to know, but somewhere, right, this is one of the results of the hydraulic analysis that Newcastle University carried out. So basically, you can see, I mean, this pipeline goes from southern Scotland to St Fergus, so it's going to go over a number of mountains, which is why the profile of the pipeline is important, and you can see what that's doing to the pressure profile in the pipeline. So I think, in terms of those, what I'll do, if you think it would be of use, is I can't just give you these presentations and put them on Blackboard because they're National Grid presentations. But what I can do is extract slides which I think might be of some use. Some of the bullet points on them could be of use, and I'll do that, and I'll get them put onto to Blackboard for you. Right, is that okay? Is there anything else that you think is an immediate issue at the moment?
Is it possible we can have the email address if some of us have some issues recently?
Of course you can. Naracon's got my email address, so by all means do that. But my email address, if you want to contact me, please don't use the Newcastle University email address I've got because I never look at it. It's jane.haswell at PIEUK, that's all one word, .co.uk. Jane.haswell, JANE.HASWELL, that's it, yeah, at PIEUK, PIEUK, all one word, .co.uk. And as I say, if at any point it's worth coming in to have another session, I'll certainly do that. But you just need to. What I can't do is commit to come in and see individuals. But if there's a group of you that want to discuss some of this in more detail, tell Naracon and we'll organise another session. But otherwise, I hope you find it. Interesting, and I hope you find it useful. And all the best with doing this and also with the exams. Okay, thank you. Thanks.
Somebody's sponsored. Somebody's on work.
He's the come and take the book.
Excuse me, just a question regarding the fatigue light. Is that a procedure specified in the standard, like how to calculate the loss of the fatigue light? Because, for example, if I use, let's say, 20% of my cycles, and then I change the pressure, I change the stress,
Yes.
the number of cycles is going to be changed as well.
It is, yes. So there's the equation, the damage equation, which is in TD1, tells you how to combine the different ranges of pressure cycles. So you need to take all of them into account. So you need for each different pressure cycle, you need to calculate the allowable cycles for that pressure range, and then the actual cycles over the allowable gives you a damage fraction. You need to calculate the damage fraction for every different set of pressures, yes, and then you add them all together.
Okay.
Okay.